The key things of this next section are the exponent and the logarithmic functions introduction. It's just your first chance to look at these. These are actually very powerful functions. They have very big implications in how we survive our modern life. I would say they're one of the big reasons that England became such a superpower and was able to rule a quarter of the globe due to their navigational abilities. Logarithms allow you to, and exponents allow you to quickly and efficiently perform very large calculations in a very effective and small focused way. We're not going to really see all that much with them. This is an introduction to them. So while I'm going to talk about these things, give you a feel for how to graph them, what you want to really take away from this is that in some other classes you're going to use them maybe. And at the very least, if you see them, you'll get to see what's going on. So here's the two things. For exponential functions, they look like this. F of x equals b raised to the x. So I've got an exponent there. Again, following my usual notation of x is a variable, and a letter like b is standing in for some sort of constant number, like 1 or 2 or 1.3 or square root of 2. The b is standing in there for some sort of constant, but I don't want to label all of them. One requirement that we have is that b does not equal the number 1. And that's just because 1 raised to any power is always just 1 again, and so this would be a very boring function. To contrast this with, I've got another equation that I've got, and this is the logarithm formula. And the logarithms work like this. I write y equals log base b of x. The way we understand this, maybe remember from our logic, if and only if, b to the y equals x. And I say this as log base b, where log is just a shortening of the word logarithm. So this is log base b, and b again will be some sort of number that I come up with and deal with. So let's look at an actual example of how something like this looks. F of x equals 3 to the x. If I want to graph this, I'm going to graph it in my usual way. I'm going to pick some x values, -2, -1, 0, 1, and 2. And then I'm going to plug them in and see what y values I get, what f of x values I get out. So I have 3 to the -2. Remember how negative exponents work? That's 1 over 3 squared, which equals 1 over 3 times 3 is 9. So I'm getting my ordered pairs. On the other hand, I have -1, so I have 3 to the -1. This is 1 over 3 to the first power, which is just 1/3. Anything to the 0 is always just 1. 3 to the first power is just 3. And we know 3 squared is the number 9. So as I start trying to graph this, I've got all these little points here. So here's what I've got. 1, 2, 3, 1, 2, 3. I've got -3, -1, 1, 2, 3. I don't know, -2 here. And I've got, let me give myself just a little bit more space here. One, 2, 3, 4, 5, 6, 7, 8, 9. So for my first point here at -2, I've got the point -2 and 1/9. -2's here, 1/9's barely above the ground, because this is, of course, the point y equals 1 up here, so it's not very high. At -1, I'm up 1/3 of the way. At the point 0, I'm up here at 1. This is my y-intercept. At the point 1, I'm up at 3. 1, 2, 3. At the point 2, I'm up here at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Over here at 2, I'm up this high. The shape is this, and this is an exponential shape. Let me see if I can actually connect some dots here. There we go. On the far left, it never crosses the x-axis. It never goes below that. One of the ways I write that is by putting some of these dashed lines here. Again, I'm not going to talk about too much what this is. These dashed lines maybe in another class you'd know would be called a horizontal asymptote. It's this horizontal line that we never quite cross. I never get below 0 because every time I plug in more and more negative numbers, it gives me a fraction that has a larger denominator, but that's never quite 0. It's always slightly bigger than 0. So this is the shape for an exponential function. As you can tell from this shape, what's happening is two things. On this part, all the places to the left of this point 0, 1, I have slow growth. As I move along the x-axis, if I think about slope, and I move from the point -3 to 2, I'm here at 1/9. As I move from -2 to 1, I'm here at 1/3. Very little change in my height, if I think about the height difference between these two. On the other hand, on this side, I have very rapid growth. From the point 1 to 2, I have a very large change in height, even though I only had a very little change in my 1 to 2 point here. So we've got this idea of slow growth, and then at some point it takes off and suddenly starts growing quickly. This means that we use exponentials to model and describe things in the world that deal with stuff like population. Populations start out slowly, small little villages, and suddenly those grow into large cities. Things in the financial market, we'll talk about in some later chapters, things like compound interest. How do you invest properly to have money for when you retire? All that stuff. Rapid growth, things that have a period of rapid growth is what's going on. On the other side of this whole process, I've got logarithms. So let's look at a similar logarithm. Let's talk about logarithm base 3 of x. From my if and only if statement, I know that's the same thing as if I have 3 to the y equals x. That's what this comment right here is telling me. I pick any x's I like, and then I have to figure out what y values I get. Notice over here, if I rewrote this, this is y equals 3 to the x. The difference between exponents and logarithms is that I've switched around where the x and y are. Here the x is the exponent part of the 3. For a logarithm, y is the exponent part of the 3. That means all of my numbers that I chose for the exponential case are just put backwards. So when I'm picking my x and my y, I just copy these all down backwards. So I have 1/9, and that gives me -2. I've got 1/3, because that was the y value, but here I'm switching x's and y's over, so what was a x value over here is my y value over here. What was a y value on the left is an x value on the right. So I have 1/3, and I get the point -1. I have the point 1, and that gives me 0. I've got the point 3, and that gives me 1. And I've got the point 9, and that gives me 2. So now I can graph these. And as I'm graphing them, I'm going to get this sort of shape. So, again, got the point -2, +2, 1, 1, 2, 3. Let's plot my points that I'm dealing with here. When my x value is 1/9, so I'm somewhere like here, I'm down at a y value of -2. When my x value is 1/3, so I'm a third of the way along on the x value, I'm at the point -1. When my x value is 1, I've got the point 0, so this is an x-intercept. At the point when x is 3, I'm up here at 1. And now on the point when x is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, not drawn to scale at all, obviously, I'm up here at the point 2. I connect these in a line and create my curve. Again, I'm not talking about this too much, but it's still here. Logarithmic equations have vertical asymptotes. And that means this blue line's never going to cross my y-axis. It's going to keep on going down this way. And looking at this graph, you can see something. For the first part, when my x values are in between 0 and 1, when I'm picking fractional x values, there's this quick growth, and then once my x values are going past 1, we have this slow growth. So logarithmic equations are used to model things that grow very slowly in general, particularly after a certain point. Not quite it's growing still, it's just not all that fast. Things that grow slowly over time involve things like information learned. And you can think about that. The first time that you show up to college, you're learning a lot of information. There's a lot of things you have to learn. You have to figure out how to get financial aid. You have to figure out where to register for classes. You have to figure out where your classes are. Over and above the actual class knowledge that you're learning, there's all of these extra things that are involved in learning the college process and understanding that. And even in a particular class, the first day of class here for me, you had to figure out how Math Excel worked, you had to figure out how Blackboard worked, you had to figure out how your book examples were going to go. There was all this extra information there. But once you actually get in the process of learning the class, it's a sort of slow and steady learning process. So information learned. And think about further than one particular class. If you look at the amount of information that maybe I've had to learn to be able to teach people, I had to learn a lot. There was all that, K through 12, there was a lot of information, all that. But now if I take one extra class, it doesn't really increase the total amount that I've learned all that much, because I've taken hundreds of classes over my lifetime. So learning is something that we can model with an exponential sort of process. Things that have a slow but increasing sort of growth. These things can be modeled. Information, I think, is probably a pretty good one for that sort of thing. So I've got exponential equations, and then since my understanding of logarithms is entirely based on this switched around version of exponents, I've got my ability to graph logarithmic equations. For today, I'm really only interested that you can graph and plot points for these logarithmic and exponential equations. That's all I'm really after you getting. We're going to talk about a couple more things, but this is an introduction to exponents and logs. I just want you to play around with them and see what their pictures sort of look like. It's mainly in other classes that you're going to get a real feel for how powerful these things are. Exponential and logarithms model everything from, on the exponential side, we talk about stuff like radioactive decay. We talk about virus spread. You want to see how a particular virus is affecting a population. Radioactive decay. We also talk about biological decay. This relates to stuff in terms of how fast you put a drug in someone, and it can be a totally legal drug, like a Tylenol. You take a Tylenol. When is it going to have its maximum effect? How long before the Tylenol's out of your system? And so you're able to take another Tylenol. Things that talk about growth in a logarithmic fashion include things like earthquake scales. We talk about the Richter scale. It forces everything to live on a 0 to 10 scale, so that's something that logarithms do. Also, maybe you've heard of decibels for sound level measurements. Again, that's something that as you start adding on decibels at the upper end, you're increasing the x value quite a bit, but the actual intensity of the sound isn't going up all that much. You get yourself out a reduction process. So we can talk about things in a decent level of measurement. These things also grow exponentially or logarithmically. So the last thing I want to talk about is a very special number. It's the number e. I'm going to use this wiggly equal sign, which probably looks about like my normal one, so let me try to put some more wiggle in there. Maybe it looks like 2 tildes almost. And this is the number that we can approximate with 2.7 if you like, almost 3. 2.71828, I think. It keeps on going. And this number e is a very special number. I told you that logarithms have a base b. And that's how you normally write a logarithm. Well, I can do all sorts of bases for logarithms. If I give logarithm the base of this number, 2.71828, that again keeps on going, maybe you've seen the number pi. Pi equals 3.14159, and it keeps on going. E is a similar number to that. They're called transcendental numbers, but that's an entirely different class. If I talk about log base e of x, we talk about this so often, rather than writing 4 characters, L-O-G-E, we just write ln(x). These are functions. It would be fair and true to give this guy function parentheses, just like I'd talk about f of x. I'd have log base b of x, log base e of x, which is ln of x. It's not multiplication parentheses, it is function parentheses. This right here is called the natural log. The L comes first and then the N because it was, I think, originally discovered in France, and I think that they switched around and called it a logarithm natural. And of course, there's a bit of a French accent into that whole thing, but I don't speak French. So I've got this log base e of x, and this gives me ln. The other thing that we commonly do is, because we live in a base 10 number system, as you know from our discussion of base 10 to base, from decimal base to binary base things, we do 10 so much that I tend to not write 10. Even if nothing's here, if no base is written, it means base 10. And this is important because if I talk about something like ln of 3 equals y, per my idea of what logarithms mean, I know that if I have log base e of a particular number, I can switch it around and get this. So if I have ln of 3, what I'm really saying is log base e of 3 equals y, which means I'm really saying e to the what equals 3. The same token, if I have log base 100 or base 10 of 100 equals y, I know this is secretly log base 10 of 100. And this means that I'm really asking 10 to what power equals 100. And this lets me solve for y. Here I know that y equals 2. Over here, since e is some number like 2.7 something, the y would be a much nastier decimal sort of number. So I can find information out about these things. We're going to use the number e. Again, it's often used for population because it's an exponential number. We're also going to see it used in financial formula for compound interest. Having this idea that you start out with so much money as your initial investment, and then you get a little bit of interest tacked on. And next, you have your money and your little bit of interest, and you tack on a little more interest, and this time the interest has to be a little bit bigger, because it's not just taking your initial principal, it's taking that interest as well as your initial principal, and together using that to calculate your interest. And eventually it sort of creates this exponential rise graph in your finances. So I think that's a good enough start for exponents and logarithms. You've got the ability to graph them and look at them, look at some of the examples I've given from the section and solve it out. Quadratic equations you don't quite have to look at in this section. We talked about them in a different place.